I see it perfectly well, yeah. Full screen whenever you want.
This is just to remind us what we are missing by doing this thing remotely, because this is one of the room of VCT Star, this one here, and this is the villa back in an 1850 photograph. Anyway, so the proton, right? The proton is nature's most fundamental bound state, as we have heard many times during this workshop. Is composed of 3 valence constituents, 2 U and 1 D quarks. It has never decayed in the nearly 40 billion years since the Big Bang, and this extraordinary long lifetime is basic to the existence of all known matter. Yet the forces responsible for its remarkable stability are not fully understood, otherwise we would be running workshops like this one. So the proton structure is described by quantum chromodynamics, which is the standard model quantum field theory that explains the strong interactions of the proton and all related objects in terms of gluons and quarks. Well, today the proton's mass can be calculated with good accuracy, but that is not the case for its radius. Indeed, as the proton is a composite object, it must have a size. The question is, how big is it? So this question is of particular importance because it is related to the question of confinement, which is the empirical fact that no isolated gluon or quarks has ever been detected. The proton radius values characterizes, therefore, the size of the domain within which the current quark of QCD Lagrangian may rigorously be considered to represent the relevant degrees of freedom of the theory. In addition, it is not just strong interactions which fill the proton size. An accurate value of the proton charge radius is also crucial for a precise determination of quantities in atomic physics, such as the Rydberg constant or the lamp shift. The solution to the standard model would deliver values for both the proton's mass and its radius. The problem is that while the relative error on the mass is around 1 part in 10 billions, measurement of the radius now disagree amongst themselves, as we shall see. But the question is, how do you measure the size of a proton, right? Well, there are 2 methods. The first one relies on measuring the cross-section for the elastic scattering of an electron of a proton. This cross-section can be decomposed into an electric and a magnetic form factor, shown here, which encode the proton shape. And then one can extract the proton radius from the derivative of q squared equals to 0 of the electric form factor. And then there is a second method, which is measuring the shift between different levels of hydrogen atoms, right? So with respect to the 0 size case, which is this potential here in red, the finite size of the nucleon, which is a single proton in the case of hydrogen, induces correction which are proportional to the probability of finding the electron inside the proton. So this potential is curved here and is the one in blue. And this, in turn, is proportional to the third power of the proton radius. Until 2010, the 2 methods were delivering consistent results with the proton radius averaging out at around 0.88 Fermi, right? However, the electron is so light with respect to the proton that it spends very few time inside it. Thus, it is definitely not the best of the probes for determining finite size corrections. A muon would be much better. As the muon is 200 times heavier than the electron, it orbits much more closely to the proton, as shown in this cartoon here. And this translates into the fact that the muon is 10 million times more sensitive probe for measuring the proton radius. So when physicists got access to muonic hydrogen samples stable enough to allow measuring the transition frequency between its levels, the situation drastically changed. And then a puzzle was born. The muonic hydrogen value was found to be 8 sigma away from the proton scattering value. And the situation didn't get any better over the years, with a notable exception, a small proton radius coming from an electron-proton scattering, which is shown here, performed by the Pirate collaboration. We will return on this later on. Meanwhile, many solutions to the proton radius puzzle has been offered, which includes that some unknown QCD-related correction may have been omitted in the muonic hydrogen analysis, that the discrepancy could signal some new interaction of particles outside the standard model, like a dark photon, leading to a violation of lepton universality, or that some systematic errors have been neglected in the analysis of the experiment. However, consider this, fitting is already hard, But having to extrapolate on top of fitting can introduce really big problems. But all attempts to refit the electron-proton scattering data so far have been called out for pitfalls and misconceptions, which seems to indicate that the resolution of the puzzle cannot be found in reanalyzing the existing data. So our idea was to avoid to cure the step in which a specific functional form to fit the data must be chosen. To this end, we resort to the so-called Schlesinger point method, which I shall refer to as SPM in what follows. So what are we talking about? In the SPM approach, no functional form is assumed. Instead, one arrives at a set of continuum fraction interpolations, capturing both local and global features of the curve that the data are supposed to be describing. So this global aspect is extremely important. It ensures that the validity of the constructed curves extends outside the data range limits, ultimately allowing for the evaluation of the curve's first derivative at the origin. So given an n pairs of real numbers, shown here, representing the values of some smooth function at a given set of discrete points, the SPM constructs the continuum fraction interpolator of those values, which is shown here. The coefficient A appearing here of the continuum fraction can be constructed recursively and ensure that it coincides with the original function when evaluated at the original abscissas. So here we show some elementary examples in which the SPM is used to reproduce some unknown function, a monopole in the first panel, a line in the second panel, and an exponential in the third panel, provided a set of input points. So as can be seen, the SPM does an excellent job in reproducing global feature of the function far from the input points. It fails only in the case of the exponential and only in the region where its essential singularity is located. But this is fine in an ideal world, but we are not in an ideal world, and we will have to consider the errors, as we shall see soon. But first of all, if the data set one is dealing with contains n data with n somewhat large, say 30 or bigger, one can then introduce a powerful statistical dimension to the method. Namely, one randomly selects a subset of n points from the original set with m typically between 4 and n over 2. Then one gets access to a very large number of different interpolation functions of the data, which is given by the binomial coefficient of n over m. And in practice, however, this number can be greatly reduced by introducing physical constraints. In this particular case, we require the interpolators to be smooth monotonic function on the entire Q-square domain with no further restriction imposed. In particular, no gauge constraint on the unit value of the proton electric form factor at the origin will be required, so we don't require f of 0 equal to 1. This will allow us to take into account the systematic errors due to the overall normalization of the form factor experimental data. The most complicated aspect, as I was mentioning before, we need to consider is that experimental data are statistically scattered around the curve which truly represent the observables, and therefore they should not be directly interpolated. Assuming that the data sets we have are a true measurement of an underlying smooth function, the solution to our problem is provided by smoothing with a roughness penalty. One looks for a description of the data in terms of a function g and a parameter lambda that trade between data fidelity and roughness as measured by the second derivative of the same function. If lambda is equal to 1, this term is absent, and 1 recovers the original data, no penalty, therefore. If it is 0, so if lambda is 0, one has a linear least square feet of the data, so we have maximum penalty. A theorem shows that G coincides with the natural cubic splines interpolant of the original nodes. In addition, a generalized cross-validation procedure delivers the optimal value for lambda given the characteristics of the dataset at n. And finally, the presence of statistical errors in the datasets can be taken into account through a statistical bootstrap procedure by which, for each dataset, we generate a certain number of replicas by randomly drawing from each datum a new one, normally distributed around a mean value which is equal to the datum itself, and a variance which is equal to its associated error. So this procedure will provide us with a way to estimate the error when extracting the radius. So let me recap. All these can be combined together to provide a well-defined procedure for the SPM extraction of the proton radius from scattering data. So we will use 4 datasets, P-red at beam energies of 1.1 and 2.2 JeV, and they combine and their combination, and the low Q-square data of the A1 collaboration. So for each dataset, we generate 1,000 replicas through Bootstrap. We determine for each replica the optimal smoothing parameter and smooth the replica accordingly. We choose M to be between 6 and 17. This gives between 1 million and 1 billion of possible interpolators, depending on N, from which we take the first 5,000 corresponding to smooth monotonic functions in the entire Q-square domain. For all N, we extracted the proton radius from each replica, averaging over the obtained 5,000 curves, and constructed the corresponding probability distribution function of these 1,000 results, which should correspond to a normal distribution. We will check that later. We next determine for this probability distribution function the mean, which we call RPM, the standard deviation, sigma RM, and then the standard deviation sigma delta M, which characterized the distribution of the 12 radii, one for each M, so extracted. So the final result is here, is RP plus or minus sigma R, where RP is the mean of the radii extracted for each M. And for the error, we have the quadratic sum of the mean of the sigma RM, so the standard deviation for each M, plus this global standard deviation for delta M, sigma squared delta M. So the question is then, if the proton radius puzzle is still standing when applying the SPM to extract the radius. But if you wanted to disprove that the proton has a larger radius, you should first of all show that you are able to reproduce it. So we can do this by showing that the SPM can reliably extract the proton radius from a variety of controlled cases and situations. Namely, we build a replica dataset from values of the proton elastic electric form factor evaluated at experimental available Q-square and generating using specific models in which the proton radius is known a priori and using Bootstrap to mimic the variability of real data. So we use 9 different generators here. We have 3 simple standard functions, a monopole, a dipole, and a Gaussian form. We have 5 parameterization of experimental data, including the one by Kelly, different series in Q-square, and its conformal mapping Z of Q-square, and continued fraction of fixed order. And then we have 1 full theoretical calculation using a combination of carrier effective field theory and dispersion analysis due to LR4. And these are, by the way, the 9 generators that have been used by the PRAD collaboration to extract their best fitters for the data they have. So for each M generators and kinematics, then we have to check the assumed Gaussianity of the radii distribution and the robustness of the extraction procedure. The latter can be proved by showing that the modulus of the bias, as defined by the difference between the extracted radius RP and the input radius as RP, is always less than the standard deviation sigma R. And then that the root mean square error, as defined by the square root of the quadratic sum of the bias and the standard deviation, is independent from the generators considered. So we have 4 kinematics, 9 generators, 1,000 replicas, 5,000 interpolators per replica, and 12 M values, which makes more than 2 billion interpolators to be evaluated. So you just need to relax and wait. And while we do so, let me show how all this work in practice with an example. We consider a dipole generator with a radius of 0.85 Fermi using the PRAD 1.1 JeV kinematics and 6 points as SPM input. So here you see the dipole generator in black, sampled at the given kinematics with the inset here, there just to show the very low Q-square part of the curve. Then you generate through Bootstrap 1,000 replicas as you sample according to a normal distribution 30% of the time, and you generate points which deviates more than 1 sigma with respect to the target kinematics, as it can be clearly seen in these figures here. Okay. Then you apply smoothing with roughness penalty. You first evaluate the best smoothing parameter, and then you smooth the points accordingly. As you see, the resulting data sets are much smoother and can be passed to the SPM. Then this is what we do here. sorry, we randomly select 6 points. We calculate the SPM interpolance and extract from it the radius. We repeat the procedure 5,000 times per replica. And then we calculate for each replica the corresponding radius as the mean of the 5,000 SPM extracted radii. And at last, we calculate the final radius and error by analyzing the PDF and the corresponding radii. As shown in the movie here, the SPM extracted radii are distributed as a Gaussian with the skewness and kurtosis close to the expected values of 0 and 3. And this procedure has to be repeated for all m's, and the results show that the calculated distribution are in fact nearly m independent, as can be seen here, which in turn implies that standard deviation, which I have defined as sigma delta m, is very small, and a similar behavior is found in all other generators and kinematics considered. Next, we calculate the SPM bias and standard error obtained when extracting the radius from all 9 generators for the 4 different Q-square ranges and statistical error. In almost the totality of cases, our procedure is robust, leading to a bias which is less than the standard error. However, for the p-rad at 2.2 JeV and the combined kinematics, the SPM extrapolation for 2 generators is only marginally stable, having a bias which is similar to the standard error in this case and in this other case here. This is consistent with the finding of the p-rad collaboration, where the same 2 generators show the highest bias for all filters independently from the Q-square binning. Notice also that the p-rad dataset at 2.2 JeV here leads to an error which is much smaller, roughly 1/3 to the one obtained from the 1.1 JeV data, and drives the error of the p-rad combined binning, reducing it to roughly 1/2 of the value obtained using the 1.1 JeV data alone. This effect, which has been also noticed by the p-rad collaboration, will be also there when considering true experimental values. Finally, we can quantify the goodness of the SPM proton radius extraction for all kinematics employed in terms of bias, standard deviation, and root mean square error. As it can be seen from any given kinematics, the MSC values are approximately independent from the generator used, which indicates that the SPM procedure for the extraction of the proton radius is indeed robust. So the takeaway message are two, and are yes, the SPM does work, and yes, it is robust. So we can now proceed to work on real experimental data. So the first data for the proton elastic electric form factor from which we extracted the proton radius are the ones coming from the p-rad experiment, which has obtained the lowest yet achieved momentum transfer square, covering at the same time an extensive domain of low Q square shown here. So when analyzed separately, the SPM gives 0.842 plus or minus 0.008 for the 1.1 JeV data, and 0.84 plus or minus 0.003 for the 2.2 JeV ones. The p-rad dataset at 2.2 JeV alone leads therefore to a lower value of the extracted proton radius and a much smaller error. This agrees with the finding by the p-rad collaboration. And when combined together, the combined analysis of the p-rad data gives finally a proton radius of 0.838 plus or minus 0.005, which reproduces within errors the p-rad collaboration published results of 0.831 plus or minus 0.008. Thus, this can be seen as an independent confirmation that the p-rad data really encode a small proton radius as determined by the collaboration analysis. We next consider the data determined from experiments performed from the A1 collaboration at Mainz. They comprise of 1,422 cross-section measured at different beam energies. And this data set stretches also towards low Q square, albeit not reaching the values achieved by the p-rad as shown here. Restricting first the analysis to the low Q square region, consisting of 40 data points, we obtain a proton radius of 0.856 plus or minus 0.014. Relaxing next the restriction to the low Q square region yields almost the same central value, but a bigger error. We get 0.857 plus or minus 0.021. Therefore, extending the momentum transfer square up to the 1 GeV square limit only limits the ability of the SPM to provide an M-independent result, as in this case we observe that the two standard deviations that I have defined, sigma delta M and sigma Rm, are in fact of the same order. So notice that the original A1 collaboration estimate is 0.879 plus or minus 0.05. I know we are missing 5 minutes.
Yes, exactly.
Yes.
This is what I wanted to say. Yeah.
Don't worry, I know it and I will make it. So we were saying the original A1 collaboration is 0.871 plus or minus 0.05 for the statistical error and 0.006 for the systematic one. Therefore, while the SPM results as a 3 times bigger statistical uncertainty, it is in agreement with both the PRAD estimate as well as the muonic hydrogen experiment. Therefore, when including the SPM results, the proton radius puzzle plot does look a bit different. According to our analysis, there is no discrepancy between the proton radius obtained from electron-proton scattering and that determined from modern spectroscopy experiment, which is shown here by the gray and the yellow band. So the SPM indicates that a possible solution for the proton radius puzzle can still be obtained through a careful reanalysis of the data in which the choice of a specific functional form to fit them is avoided. The SPM also circumvents all the pitfalls identified in previous data reanalysis, and in particular, it is the only method in which cutting data sets to small q-square does make sense, whereas for a fitting procedure, it has been shown that it makes the balance between bias and overfitting harder to achieve. But perhaps the bigger strength of our method is that it stays the same independently from the data set that we need to examine. Suppose, in fact, that we were to apply the same procedure to the pion case, the available experimental data is in this case constituted by 2 data sets collected in 1984 and 1986 by the NA7 collaboration. They provide the negative pion electromagnetic form factor on a not so low q-square domain shown here. One can check that the procedure just described in the proton case is robust also in the pion case, even if with the larger biases as shown here, because which are certainly due to the fact that the data have a lower overall precision with respect to the PRAD ones. However, from the actual data, when we use the SPM to extract the radius, we get 0.649 plus or minus 0.012 for the 86 data and 0.638 plus or minus 0.009 for the 84 data. These results are smaller but compatible with the original radii obtained by fitting the data with a dipole functional form. In addition, which are shown here, Amendolia 86 and then Amendolia 84. And in addition, the 1986 data result is compatible with the PDG average, the PDG 2020 average, which is 0.69 plus or minus 0.04 Fermi, which indeed has been evaluated, consider only the 86 NA7 data. So, contrary to the proton case, the SPM reproduces the pion radius, which is nice, as it shows that the method does not see smaller radii when there is no need to. But here there is a plea to our experimental friends, and it would be great to have denser data that extends more in the low q-square region, with which a more precise determination of the pion radius would become possible. Not to mention the Keown case, because there the available data cannot be analyzed at all through these methods. So for the Keown, we are really at square one. So finally, let me end by considering the Deuteron case, as there is also a puzzle there, which is not extreme as the proton one, but still there is some discrepancy. Let me notice that in this final example, we are playing a different game. There are no data in the low q-square region, and so we will use the projected measurement from the DRAD experiments, which reach down to the QRAD q-square region, which is shown again here, and have a beam-by-beam uncertainty which varies between hundreds and tens of percent as shown here. So the DRAD collaboration has tried to determine the best fitters for the projected data, testing 13 models, 4 parameterization of the experimental data, and 9 theoretically based models. However, as following the same procedure used in the PRAD, none of the tried fitter was robust, as shown here, because if you see, it is completely bias dominated because the bias extends up to 0.003, 3, whereas the variance is below 0.09. So as following the same procedure using the PIRAD, none of the trial filters was robust, I was saying. They resorted on a smearing procedure for the 4 models based on the experimental parameterization and determined 2 possible robust filters, which are shown here, which are the F rational 1.3 and the mod rational 1.1. None of them is, however, the one chosen in the PIRAD analysis. However, if you apply the SPM, we do not need any change in the procedure. The SPM provides a robust extrapolation for almost all models when using the 1.1 JEV or the combined kinematics. The 2.2 kinematics is useless in this case because the errors are too small. And it has a performance in terms of bias and error, which is compatible with the one of the best filters found in the DIRAD collaboration. And having said that, I leave here a summary slide of our results, and thank you for your attention.
Thank you very much, Daniele, for your presentation. The session is open for questions. Okay, I can ask one. Maybe it's because I didn't understand correctly, but the SPM extraction of the protons radius with the experimental data from Mainz.
Yes.
So you get a larger value because you reach because they have data at Q square equal to 1 GeV square. So I think that you did something there, no? I mean, you analyze separately low Q square and all the data set, something like that?
Yes, exactly. But the problem is not really, I mean, the difference is basically is in the extension, you see that the PIRAD data go much lower in Q square, right?
Yeah. And
also there is the spacing of the data. The spacing of the data determines the amount of smoothing that you have to apply. And the spacing in the PIRAD data is lower than the spacing in the GA1 data. So it's a combination of 2 things, low Q square and spacing of the data.
And then for the pion, looks like there is no experimental data for very, very low momentum transfer, as in the case of the proton.
Exactly.
And then in fact, you don't get any disagreement there with all measurements, isn't it?
Well, it's not because of that. I mean, it's just because what you get is a much bigger error. You see the error here.
I see.
And in percentage, I mean, is much bigger. But yes, I mean, it would be great to have a lower values in Q square because, as you see, the data are quite poor there. But the spacing is okay. The spacing is okay. So when you apply, you get the same extrapolation that these guys got with a normal dipole, which might tell you that the dipole works. Actually, if you see here, the dipole is the one that has less bias also in the SPM analysis. So if you use this data, the kinematics of this data set, and you try to extract the radius from a simple dipole form, you get basically 0 bias. You get it on top, which is why basically we get the same results here.
Reinhard, yes.
I guess it's now more a question to Jorge's question. If I understood you correctly, what you are saying is that between the lowest Q squared value of the A1 experiment, below this, and of the PIRAD experiment, there the form factor still changes significantly in its functional form, especially in slope and curvature. Is this what you're saying? That if you really look precisely what to extrapolate, and you would not plot the form factor, but slope and curvature, you would, for example, see still a variation in the curvature. It would not go precisely to 0.
Well, you know, I mean, I don't even look at how the thing looks like in the low Q square region. I mean, I don't even look at the interpolators that I am extracting, right? I just get the value that they give me. I mean, these guys can do whatever they like. They have just to be monotonic, right?
Yeah, but
So, so I cannot answer to the question in the sense that, I mean, I get something statistical there that tells me that the curvature can be that plus or minus that one, right? Now, for sure, the two data sets looks different. I mean, there is also this plot that I think Oleg was showing. You remember that one looks a lot flatter than the other one.
Yeah.
Right?
Yeah.
So, but yes, I didn't analyze. I mean, I am a little bit agnostic about the data there. I just try to see if what the data tells me, and this is the range that they tell me. If it says to me that the curvature there between the two varies a lot, well, if that is your question, yes, it looks like that. Yes.
Yeah, which is a little bit of a physics puzzle. What should change in the physics at such low scales, right?
Yeah, correct. Yes.
Yeah, okay, thanks.
Thank you. Well, I do not see any other questions, so let's close the session here, and thanks all the speakers again. See you at 4 p.m. in 25 minutes.